All right, I think we're going to go ahead and get started. Before I introduce today's speaker, just a word about our next speaker. In 2 weeks, on April 9th, it'll be our last speaker for this semester, and that will be Professor Aaron Stebner from the School of Materials Science and Engineering. That's very loud. Sorry, let me turn that down just a bit. Okay, better. All right, so it's a real pleasure to have with us today Professor Vida Jamali from the School of Chemical and Biomolecular Engineering. Vida got her bachelor's degree in chemical engineering from Sharif University of Technology, then her PhD in chemical and biomolecular engineering from Rice, and then did a postdoc in chemistry at UC Berkeley. She came to Georgia Tech, where she's currently an assistant professor in 2022. She's won a number of awards, most recently an NSF Career Award just this year, and an ACS Petroleum Research Fund Doctoral New Investigator Award last year. And with that, I will turn it over to Vida.
Thank you. Thanks for the kind introduction, David. Thank you all for joining. Today I'm going to talk about imaging, learning, and engineering of nanoparticles dynamics using liquid phase transmission electron microscopy, which is one of the main techniques that we are using in our lab to characterize nanoparticles dynamics. My name is Vida. I'm a new assistant professor in the School of Chemical and Biomolecular Engineering. So what I'm going to talk about today is a story that starts with some work that I did in my postdoc lab. And then when I started here at Georgia Tech, we continued in that direction and some of the new ongoing directions that we have in the group. What got me into this field of using liquid phase TEM was that I was a soft matter scientist by training. I was looking at material systems that have certain type of material building blocks. And so I would characterize these material properties, mainly things like composite materials, you can think of it. So we wanted to tune their mechanical, electrical properties. I know why this is happening. So what then I started to think about was that is there a certain structure in these material systems that we need to basically look at their nanoscale components. Okay, let me. I think it's the adapter because I tilted it, but hopefully it's stable. Okay, so I wanted to characterize the material properties of the system, but I started to think about that at a time that there is a lot of dynamics within the structure at the nanoscale that you want to be able to characterize and study that in order to be able to tune the material properties at larger length scale. For example, interaction of a nanoparticle with a polymer environment around it determines the mechanical properties of the composite material that you're making. In some cases, we want to understand these sort of interactions and dynamics at the nanoscale. Great example of that is biological systems. We have these machineries in soft and biological matter called proteins, and they change their conformation, and through that, they perform some functions in our cells. So we want to understand that in some cases, and in some cases, we want to mimic that or even come up with completely new material design architectures in order to perform certain functions. Example of that is nanorobotics, nanoemulsions, or nanoelectronic devices. But we want to be able to characterize these dynamics and interactions at the nanoscale. And when we talk about this sort of dynamics, we're talking about in terms of spatial resolution and temporal resolution, we are talking about the length scale of about a nanometer that is comparable to the size of our nanomaterial building blocks. And in terms of the time resolution, we are thinking about millisecond, which is sort of the time scales that these dynamics start to show up. But when we go back to the imaging techniques that we have, for example, optical microscopy, it is fantastic. We're using every day all sorts of different forms of optical microscopy. But it is limited by the Abbe diffraction limit, which basically tells you that you cannot use visible wavelength light to resolve features that are smaller than 200 to 250 nanometer in size. And then there was, of course, the advancements in microscopy coming up with super resolution microscopy, which got the Nobel Prize in chemistry. And these methods are based on the entire principle is that you have fluorescently tagged particles or nanomaterials in general, or it could be biological materials, and you are exciting them with a laser. But you can, for example, in case of a storm, you're doing this stochastically so that you can resolve structures that are very close to each other. And by that, I mean as close as 20 nanometer in distance. And to achieve this, you need to collect a lot of images. And these images, that as you fluorescently excite them on and off, and then sum them to build one high-resolution image, one high spatial resolution image. So you're sacrificing your temporal resolution to get to the spatial resolution. So we don't really have the temporal resolution we need, but we have a spatial resolution about 20 nanometer. What would ideally work for us in terms of the spatial resolution we are looking for is something that works with the electron beam, because easily it can give you that spatial resolution. But the challenge in using TEMs for looking at nanostructured systems is that if you are interested in dynamics like me, then if you do normal TEM, you're drawing your sample overnight, so there's no dynamic into that. And if you're doing cryo-TEM, then you're vitrifying your solution. Again, there's only one static image. So how can we really use TEM to look at the dynamic phenomena at the nanoscale? And this was the question that people have been thinking about it for a while, but during the past decade, we have now a technique that is very well established called liquid phase TEM that we're mainly going to focus on today. And it allows us to explore all these sort of dynamics that exist at the nanoscale in the solution environment, but using a TEM. Of course, you're losing a little bit of a resolution because you have a thick water layer, but it is a TEM. So you're really looking at a nanoparticle here, about like 60 nanometer in length. The idea of using TEM for looking at liquid samples started back in 1944. The first paper is a closed cell for electron microscopy work that was done at Stanford, that they were thinking of how can you, for example, have a polymer film or a formavar and then put liquid in, encapsulate it, put it in a TEM and look at it. So the idea existed. We all knew that we can encapsulate a liquid sample and put it in TEM so that we can look at the nanoparticles or materials that are in the liquid phase. But it wasn't until 2003, 2006, and that Francis Ross at IBM started to think about, okay, can I make these microfluidic sort of channels and then put that in the TEM, and I can put my solution in there and look at the dynamics of nanoparticles. So that was the start of designing these silicon nitride-based microfluidic devices that has the silicon nitride membrane that is transparent to the electron beam, and you can look at the sample that is within the chamber, and it is protected from the vacuum. And then a little bit later, in my postdoc lab, I started to look at can you actually do a simpler approach, take 2 graphene sheets, and then put a liquid droplet in between, sandwich it, and you make these pockets that encapsulate the nanoparticle, and then with that, you can actually resolve these 3D structure of single nanocrystals inside these graphene pockets. And then now, flash forward to today, and we have these commercialized silicon nitride liquid cell holders that have all sorts of capabilities. So it is not only that you can look at the dynamics inside a chamber that has silicon nitride window, but you can also in situ heat the sample, the liquid solution. You can do electrochemistry experiments, so you can monitor the electrochemistry of the solution. And these are all in a commercial form. So you just purchase these silicon nitride e-chips and you use one of these specialized holders and do the experiment. And with this, basically the geometry of the setup is that you have this small chip and you have one of the large chips. This is a video from Protochips company, one of the companies that make these. There's an O-ring, and then the bottom chip sits, and then there's a liquid in between, and you put the lid on, tighten the screws, and that protects the liquid from the vacuum. Now you can heat up the sample. You can also, once you put this on a normal TEM, so you don't need any fancy TEM, it's just a normal TEM, but it needs to be adaptable for these liquid cell holders. You can flow in and out the liquid, so it's sort of like a microfluidic device. And there's 1 outlet, 2 inlets, so technically you can also do in situ flow mixing if you want to flow 2 different, you want to start your experiment with 1 component in the solvent and then start to flow in a different component. And once you have that, then you can also use the electrodes that are microfabricated on these e-chips and do basically collect the IV curves and do electrochemistry measurements, or also heat up your sample in situ and look at the response of your material system to the heat inside the liquid environment. So this is exactly the setup that we have here at Georgia Tech. And once I arrived here, what we started to think about is like what other people are doing with these techniques is that one of the approaches from one of my colleagues, Chen Chen, is that using this technique for looking at self-assembly of nanoparticles of different shape into superlattices. This could be triangular particles, spherical particles, and probing the effect of environmental conditions like the ionic strength or pH of the solution on the self-assembly. So can you modulate the self-assembly of these nanoparticles? There has been also work in observing in situ the formation of certain nanomaterials. This could be single nanocrystals, growth, or it could be MOF materials. In this case, these are zeolite imidazolate framework 8 that you can see how they, you can observe in situ the formation of the MOF. And there are a lot of questions that we either had the 0.0 or 0.100 when the material was made before, but now we can observe all of the growth process in situ, especially if this is a solution phase growth. And so the other work that I really like is that when you can modify the commercialized in situ holders to use graphene cells with that, and then you can basically now start to look at the single nanocrystals, resolve the 3D electron density map, and from there you can reconstruct the 3D structure of these single nanocrystals. Of course, this is inorganic nanoparticles in this case, but what excites me about this work is that it opens up the idea that, okay, can you actually look at all sorts of different nanoscale materials? Can you look at single particle reconstruction from protein molecules? So these are the directions that not only I'm interested in exploring, but also I know that other groups have been started to looking at these problems. So there is a lot of potential in using this technique. What we started to do was, can we develop this technique as a single particle tracking method? So we are interested to looking at how these particles interact with their surrounding environment and how do they move, and from there basically infer what are the material properties of their surrounding environment and characterize the environment that are surrounding these nanoscale particles and engineer them in cases that we want. So what we do is that we take the TEM and then we have the liquid cell, commercialized silicon nitride liquid cell E-chips, and we put our nanoparticle that we synthesize in different shapes, size, or surface chemistry into this solution, and then we collect videos from the motion of these nanoparticles, which then we analyze using the algorithms that we have developed in our group, and then we arrive at these spatiotemporal trajectories, which are like thousands of points of coordinates of the particle in time. And then we start from there to think about, okay, what sort of chemistry and physics we can extract from these spatiotemporal trajectories. And by that, I mean, can you characterize the interaction of a particle, for example, with a polymer environment that is surrounding it? So to do this, I'm going to say something that it is not as simple as this. So when I started to approach this problem, I started to think about that if you want to, as a chemical engineer, learning how to work with liquid phase TEM, I started to think about the electron beam of the microscope that allows us to visualize all these dynamics. We need to also understand how this electron beam is interacting with the system that we studied. And so the first step in using the liquid phase TEM for single particle tracking is that understanding and controlling the effect of electron beam on the system. And once we have that, then we can go ahead and use it as an engineering tool. So what I'm going to mainly talk about today is that answering this question of how does the electron beam affect the dynamics of nanoparticles, in particular motion of nanoparticles in the liquid phase TEM. And to answer this, I'm going to talk about our work that I started in my postdoc and on looking at the motion of single gold nanoparticles that are about 60 nanometer long and 20 nanometer in diameter in aqueous solutions, and exploring the effect of dose rate on the motion of nanoparticles. And this is a direction that we've continued in my group since I joined here at Georgia Tech. And this work was should be accepted, should be out very, very soon. And then once we have that understanding, we can go ahead and then use the electron beam as a tool for engineering, which is another direction that my group is right now exploring. But I started also on this in postdoc and thinking about, can you use the electron beam to do in situ liftoff and then assemble nanoparticles into different form of self-assembled structures for different sort of applications. And now we are taking this into guiding nanoparticles in situ in form of like nanomachines. So now, to start, let's look at two videos. One of these, there's from exactly the same batch of nanoparticles, 60 nanometer long rods, dispersed in water. They have CTAC ligands. And we look at these videos that one is collected at dose rate of 15 and one is collected at dose rate of 35. So one thing that it is very clear when you look at these videos is that as you increase the dose rate, the particle moves faster, but not just faster, it also moves further. So you explores also the frame, but the other one on the left-hand side is sort of like stuck in one single point. Now, if I analyze these trajectories and show you in the same time frame and scale them to the same, so show you the spatiotemporal trajectory of these particles, you will see that these definitely the diffusivity of the particle increases from left to right by increasing the dose rate from 15 to 35. So the diffusivity for sure increases, and that's about like how many nanometers it travels during that time. Let's think of it. Now, if I magnify these trajectories, then I'll start to see that it's not just the diffusivity that increases, but also the diffusion pattern seems to be changing, and that's then open up this question of, does the electron beam actually changing the diffusion mechanism of nanoparticles, which is the question that we started to answer first. That when we think about the particles as being increased at dose rate, we collect these trajectories, but the challenge is that even though you have terabytes of data of images every time that you do the experiment, once you analyze them, you arrive at certain spatiotemporal trajectories that are only kilobytes of data. And at that point, you only have access to about, like, for example, 20 trajectories. So you do not have a statistically large enough number of trajectories from the liquid phase TEM experiments. And it is very hard to use canonical statistical tests to conclude any sort of information about if the diffusion mechanism is changing, and if it is, in what form. So what we started to do was that we collected a large data set of nanoparticles motion across dose ranges from 2 to 49. And this is an example of some of the trajectories. These are the same one that you're looking at the magnified version. The only thing that you can see is basically that the diffusivity for sure increases. The diffusion mechanism is also evolving with the dose rates from 2 to 40 to 50, sort of electron per angstrom square second. So once we collect all of these trajectories from LPTEM experiments, we analyze them. At the end, what we have is a matrix of x and y coordinate of the particle in time, which we're going to treat them separately, x and y separately. And we've designed this convolutional neural network. The algorithm that we designed is called MotionNet or MoNet, and it is not just applicable to liquid phase TEM, but it is applicable to all sorts of microscopy. It is trained on ideal stochastic processes, that what you would expect for nanoparticles interacting with different sort of environments to move, like if the simplest is Brownian motion that we all know about. But if there is a heterogeneity in the system, then you start to see other types of motion, including continuous time random walk, where the particle interacts with the potential wells, which could be a polymer environment that has certain affinity with the particle, or it could be fractional Brownian motion, which is another type of a stochastic motion that when you have a very slow diffusion in a viscoelastic medium. So we simulated tens of thousands of trajectories and trained the neural network on these, knowing the ground truth behavior. And once we feed these our experimental data into the neural network, we can then output the probability associated with each of these classes of diffusion. So with what probability you have continuous time random walk, FBM, or Brownian motion. So once we applied this neural network on our data, what we could see was that as we increased the dose rate from 10 to 49, there is a change in the diffusion class from fractional Brownian motion to FBM, and on average. So each pie chart here is showing the average behavior for each nanoparticle. So we have, in total, we had 40 nanoparticles that we looked at them. We collected a lot of trajectories from these, but we chopped them into pieces. And I'm going to talk about it in a second, why this is useful to look at them in pieces. And then reported an average behavior for all pieces from that nanoparticle. So 40 pie charts total. And it is very clear that we have this transition from green to blue with increasing the dose rate. So now we could also, of course, go ahead and benchmark our results with some of the canonical statistical tests that exist in the limit that we can actually conclude anything from them. But it seems to be valid that we see this transition. Very good, very nice. But then we started to think about, okay, how is the environment then changing if that neural network is showing this transition in the behavior? And the hypothesis that at the time we came up with was that we have this silicon nitride membrane in the liquid cell chamber that naturally have these silanol groups that are negatively charged. And then we have an aqueous environment that at low dose rates, probably these the molecules of water are doing hydrogen bonding with these silanol groups, forming a viscoelastic layer next to the surface. And the particle is interacting with these silanol groups on the surface, and because of this viscoelastic environment that exists very close to the surface, then particles start to behave as if they are moving in a viscoelastic media, which is similar to the fractional Brownian motion. But as you increase your electron beam dose rate, then there is radiolysis in the liquid chamber of the liquid cell TEM that forms. And because of that, then you start to have these H pluses that are formed, and they're interacting with the silanol group and passivating some of these silanol groups that are on the surface. So when that happens, then you have less of an interaction of the surface with your positively charged nanoparticles. And so every now and then these particles get trapped close to one of these the group of these silanol molecules, get trapped and then move a little bit, and then after a while their thermal energy is enough to get them out of these well to move to another one and another one, and that now resembles the diffusion on a heterogeneous energy landscape, which is consistent with the CTRW picture. So even though this picture is very valid, like consistent with what we get from the neural network result, then what we started to look at was that if we pick one of these trajectories, for example, from this middle dose rates, we see that from the Monet algorithm, we get the result that it is like with a good probability, this is a fractional Brownian motion, almost 75%. And with some probability, it is also continuous time random walk. But what does that really mean for us? The beauty of the algorithm that we developed is that we can chop our trajectory into pieces and look at the behavior of the trajectory all through these pieces. So when we start to look at each 300 frames separately, we see that the type of the diffusion class is evolving throughout the trajectory. So it starts from somewhere, and then it switches from, like, for example, from FPM to CTRW back to FPM. So some regions, the probability of CTRW is high, and in some regions, the probability of fractional Brownian motion is higher. So it is really a true mixture of these. But then the question is it really the mixture of these phenomena, or is it something that is of its own, and we don't have any closed form equation to describe it? And the clue to that is that if we embed all of our trajectories and all of the simulated trajectories that we can simulate, that we have unlimited amount of them, into a low dimensional space using this t-SNE test, or like similar to UMAP, any other PCR test, anything, PCA test, sorry, anything that you want to do. But what you will see is that the CTRW ones are clustered on one point, fractional Brownian points are clustered on another point, but liquid phase TEM data is all over the place. So it's not really fractional Brownian motion or continuous time random walk, or just simply a mixture of these two, but I mean, with a certain contribution from each class, but it's all over the place. So what if that there is one sort of a model that could describe it, but we do not have access to that closed form equation? And that is something that is not only observed about nanoparticles interacting with environments. It has also been observed in polymeric environments when nanoparticles interact with the polymeric environments, also in protein molecules moving over lipid membranes. So this is a type of problem that has been revisited over and over in the literature throughout the years, that even though we have access to these stochastic models, they're not necessarily enough sometimes for describing the type of diffusion that we observe in experimental data. So to then solve this problem, we started to think about, when I started here, that can we design a neural network or AI model that can learn the physics from our data, but also be able to generate new type of data very similar, basically identical to the data that we get from liquid phase TEM. And I'm going to talk about why this is useful if we have this model. But what we did, in short, is that we designed a variational autoencoder model here, that the loss function of these variational autoencoder is informed by the physics, I mean by the statistics of the trajectories, that we knew what sort of characteristics they should have. So we helped the neural network to learn those characteristics better and better. And the beauty of this model is that when you encode all trajectories, a mixture of simulated and experimental, so we have thousands of data from simulation and experiment, and we encode them into a latent space of very low dimension, you're basically passing all your data through a bottleneck, and by doing that action, and then reconstructing it, you are learning the essence of the physics of these trajectories. So you have a model that learns the physics of this data, so you basically have a black box simulator. So what it can do is that basically if you input a CTRW FBM Brownian and encode it, it can then later generate these trajectories for you that have exactly the same sort of a statistical properties as the data that you would collect from any of these. So not only the ones that we have closed form equation for, but things like liquid phase TEM that we do not necessarily have a closed form equation for. And so we when we start to think about, is there anything specific about this neural network that it can learn all sorts of the statistics from the data? So what we did to analyze this was that we started to look at by LV here we mean the latent variable. So the latent space has certain dimension, which we call each of those a latent variable. And we started to simulate trajectories with different anomaly exponents, so different level of subdiffusivity, and then look at how the behavior of these trajectories are, as basically the anomaly exponents change, how the latent variables are responding to that. And what became clear for us is that there are two of these latent variables that pick the characteristics of these trajectories. One is very sensitive to the continuous time random walk, and the other one is very sensitive to the FBM sort of behavior. But in general, that means that there are latent variables in this latent space that can learn that subdiffusivity from the data and can basically, we can tweak them in order to generate new trajectories by playing with the value of those latent variables. And that's exactly what we did. We went back and said, okay, so what if now we want to generate an unlimited amount of data from liquid phase TEM? I can't afford to collect many data sometimes. The videos are very heavy, each of them a couple of hundreds of gigabytes. And so what if for some purpose I need a lot of data? So now I have a black box simulator that I can basically tune the values of these latent variables and change the level of the subdiffusivity and change the level of anti-correlation that these trajectories show by just tweaking these values and basically exploring latent variables from left to right to top to bottom. Like we are playing with the value of the latent variable, and as such you get different trajectories that have different sorts of behaviors. So starting to see this noisy behavior is representative of the fractional Brownian motion. The big jumps that you see here is that the resemblance that they have to the continuous time random walk processes. So now with this, then we started to think, okay, the application of this that we are looking for is that one of the ideas that goals that we have in our group is that can we move beyond having TEMs as just passive characterization tools into automated experimentation tools. And that's a direction that my group is right now working on. And what we want to do is basically put AI in the loop of microscopy. One the reason that the black box simulator is useful is that you can explore these latent space by picking different points. And you look at one single trajectory while you move from one point to the other, the behavior of the trajectory starts to change. So you have a model that can, by traversing this latent space, can tell you how the nanoparticle supposedly should move inside the liquid phase TEM chamber. And once now you have a particle that the motion responds to the electron beam, then you can tune it, like how you can basically, can it move in a different way? Can it get closer to a different spot on the liquid cell chamber that you want? And this basically puts us back into the picture of like, if we want to use the electron beam as a tool for engineering inside the liquid phase TEM, is there a way to guide the nanoparticles motion using AI models on the TEM microscopes? And to give you an intro to this, why we are thinking about this problem, I'm going to talk about a work that I started, a collaborative work that I started doing in my postdoc, which was on using the electron beam to tune the assembly of nanoparticles. Not just assembly, but literally also the motion. And what we're doing in this case is that we take the silicon nitride E-chips, and instead of loading a liquid solution with nanoparticles into the chamber, this time we're going to nanofabricate, basically using lithography, these particles, these rod-like particles on the surface. So some of these rods are attached to the surface with titania, and some of them are attached with chromium. And the reason for the choice of these two materials is that from previous experiments, what we knew was that titania is a material that is very resistant to the hydroxyl radicals that are going to be generated once you shine the electron beam at high dose rays into the liquid cell chamber. But chromium etches away very easily. So if I have a bunch of particles that are on the surface, and when I add water on this, close it, and put it in the microscope and shine the electron beam at high dose rays, I'm talking about more than 100, then the chromium starts to etch away, and the rods that were attached to the surface with chromium are going to be lifted off the surface and start to move within this array of fixed nanorods. So you make this synthetic energy landscape on the surface of the silicon nitride, and then the particle starts to move, and depending on what sort of interactions and surface chemistry the particle has, it starts to interact with the neighboring rods. In this case, these yellow rods are the fixed array of nanorods, and the red rod is the mobile nanorod that you can do in situ liftoff with. So what we call this method is the in situ liftoff. And then what we can do is that we can study the interaction of these mobile nanorods with this fixed array of nanorods around it, and go back to the theories that explain the interaction of one single nanorod in a fixed energy landscape with certain charge density, and also with the bioscreening length, and back calculate what would be those interaction parameters. So basically, what is the bioscreening length, what is the charge density, and once we have that values, we can go back, and this time, when we go to the nanofabrication room, we can make these rods in a certain forms that we want. Like, for example, we can make arrays of different spacing. So the only difference between these two cases is just the spacing between in the horizontal spacing between the rods. And what we end up seeing is that knowing that in a predictable way how should they interact with each other, we can get different sorts of self-assembly behaviors. So in configuration A, the particles are forming these like sort of zigzag structures, while in configuration B, they do the head-to-head assembly and assemble in a different manner, just by playing with the spacing, nothing else. The solution, the rods, everything is the same. So that allows us now to do, if you can think about like where does this idea go next, would be that if you want to make, for example, a nanoelectronic device, can you actually use the in situ liftoff method to assemble particles into certain structures that you're interested in, which could be as simple as a transistor, with different, not just gold nanoparticles, but also including semiconductor nanoparticles. But that's just a beginning to thinking about TEMs are not just passive characterization tools, but they're engineering tools, and not just a simple engineering, but it could be also an automated engineering tools, like robotic experimentation tools. And so once you have particles that respond to the electron beam, this case is just because they're you can etch off the base of the nanorod, but in cases that we are continuing to work on right now in my group is that we have particles that actually their motion responds to the electron beam of the microscope. And so we can guide their motion by manipulating the electron beam of the microscope. So now with this, I want to thank you all for joining, and I also want to thank my group. Especially a lot of things that I showed here was Zane's work, and Isabel has been recently joining my group, and she's now working on the ideas related to the last part, engineering of the nanoparticles motion. And I want to also thank the funding agencies, including the IEN 1000X, which is helping us develop new forms of liquid phase TEM to study nanoscale materials, and all our collaborators with some of their work I showed here today. And I would be happy to answer your questions. Thank you.
We have plenty of time for questions.
I usually talk very fast, so
You do.
How thick is the microfluidic channel?
So you can purchase them with different levels of the spacer. So the minimum that they're made is 50 nanometer. The maximum is 1 micron. But at 1 micron point, it's very thick. So unless you have a very big object that you're looking at, our to-go spacer size is 150 nanometer. But that's only at the edges, because once it goes in the vacuum, it bulges a little bit. So at the center, you always have thicker up to a micron.
As the nanoparticles moving around, it's not having to refocus or anything?
So these particles that I talked about are mostly interacting with the membrane. And so most of the things that we have done so far is just particles that are very close to the surface. And so we don't have that much of a focal plane change. And once they are, and the reason that we can see them with the cameras we have, which have millisecond resolution, is because they're interacting with the surface. If they're moved away from the surface and they go in a bulk, they're going to be moving orders of magnitude faster than what you can catch them with the cameras that exist today, which is the idea of the IEN proposal. Like, can we go beyond that?
I see. One last question. Are you able to image, say, proteins moving in solution?
That is something that we are working on right now. But yeah, I'm not just completely in the bulk, but even close to the surface. I think that's how you can, at least we're thinking that we can do 3D reconstruction without doing cryo.
Cool.
Yeah, and maybe as a follow-up question to that, so maybe I missed it. Have you done any imaging besides gold nanoparticles?
Yeah, and right now here at GT, we've been starting to look at biological systems. Okay. There has been work on other energy materials. People have looked at battery materials before, but what we have so far is just gold and biological samples.
Okay. Other questions?
Thank you for the talk. I have a question about how you find these samples. Is there a lot of them in a relatively large volume, and you just randomly see something, okay, this is interesting, let's see what it is?
So the sample that you load into the liquid cell chamber is about a microliter. So you have about a microliter, and so you can sort of calculate how many particles you should have based on if you do UVVs before the experiment. It should be not like for the thing that we do, like single particle tracking. You don't want it to be concentrated, so concentrated that they're interacting and self-assembling, which is things that other people, like Chen Chen's group does that I showed earlier in the superlattice formation. But what we are focused on is diluter solution that you can identify particles individually. You move around and you see them. Usually you see a lot of them, especially at the corner of the liquid cell chamber, because it's a thinner, because of the spacer. You start to see a lot of them moving. But it is not too complicated if you have a middle level concentration.
Thank you.
You're welcome.
Other questions? All right. If not, let's thank our speaker one more time.
Thank you.